We're here today, and the topic of this conference couldn't be more on the money in what is being discussed in the fields of cognitive neuroscience, social neuroscience, neuroscience, philosophy, the whole issue of the meaning of morality and how it is to be understood from a scientific perspective. What you're going to hear, if I was giving a talk on morality, is pretty much the research of those who are here to talk to you about it. So you have a feast ahead of you. And if I was to capture what you're going to hear quickly, I would say that people will argue to a large extent that a lot of our moral judgments are universal and made by all members of our species. That the neuroscientists will come in and say that probably the decision to make those judgments occurs before you're consciously aware of it. And that for some reason, every one of us gives a different reason as to why we all behave the same way. And that putting that all together, nonetheless, the question becomes, does that mean that we're not personally responsible for our actions? And I would argue the answer is a big fat no. But I'm not going to talk about that, because they are. And what I'm going to talk about is this question of what brain science and neuroscience can teach us about the nature of beliefs, belief formation, how it occurs, and give you a sense of what the underlying brain mechanisms might be. And I will pull it together with an idea at the end that because we are belief-creating machines, we humans, that by setting up a belief, a strong belief that we all possess, that we are unitary agents making choices on our own, that might in fact influence how the brain does its business. And I will tell you what I mean by that. Now, we all know that we are belief-generating machines. The beliefs that exist for religions, that are religions throughout the world, are clear and well known to everybody. And what's interesting, if you take a map of the world and look at all, you will see that well over 95% of the species have some kind of belief. I think there are 4,100 religious beliefs now, with a few being largely dominant, as you know. So we like to make beliefs have explanatory models for what is going on around us and what the meaning of life is all about. There can be no argument about that. And it all has to do with this thing, which is the 24/7 brain, I call it. This is a picture lent to me by Mark Rakel on the intrinsic activity of the brain. This is what your brain is doing now as we sit here in this hot room. There's air conditioning here at Holy Cross, but there might be a good idea. The brain is in constant motion, constant activity, constantly computing and establishing decisions and creating baselines of activity and all the rest of it. It just can't go to sleep. It's just constantly working. And what we know is that through a long and fascinating history of neuroscience, clinical neuroscience, basic neuroscience, we really know that we have a large, what is called parallel and distributed systems. There's activities, a gazillion of them all over the brain doing their work with profound effects locally and at distance in the brain. And so we have this view that we have a large parallel and distributed brain that's constantly moving and exchanging information both locally and long distance. And you can now get in and actually look at the connections between the various hubs, as they're now called, that are alive with activity. And this system is that way. It's just kind of, you got to come to grips with the fact that that's what our brain is and how it's built. But none of us believe that there's a million little things in there making decisions. We make the decisions. There's a big you in there. There's a big big number one in there making all the decisions. And we believe that very strongly, and everybody in this room believes it, and I believe it. But what's really going on? You know, the world is not flat, get over it. And the question is, how are we to think about this? And so one of my favorite little demonstrations is that we have the homuncular theory. There's the little guy in there making it, and you can see it here in this little demonstration where it looks like an integrated piece of music is being self-generated and everybody's enjoying it, but as the cameraman here starts to snoop in and take a closer look at the model, indeed he finds something very interesting, and you can begin to see it right here, the homunculus. There's the woman playing the organ that is making that music. And we have that model, we hold it dearly. Dan Dennett, the philosopher, lent me this film clip to make the point. And I want to make this point because it's so important to where we're going.
Look at this.
What the hell is that?
There it is. The big lever puller in the sky. So here we go. And what we're moving to in modern neuroscience, as I've tried to outline quickly, is the fact that we come with this machine and it's turned on and it works. And it plays a tune and it can do many different things if the machine was a little more programmed in a little more complicated way. And the question is, how do we understand that? How is it we can, on the one hand, continue to make advances in the mechanisms that underlie the perception and cognitive reality of our lives, and on the other hand, dismiss it and believe that we, in fact, are a unified agent carrying out all our will. And I would like to make an argument that it has to do with a particular one of these systems, one of these modules, one of these local systems that are continually found and discussed throughout the brain. It has to do with one called the interpreter, and it basically is found in the left hemisphere of the human. And this is the system that collects information from all the activities of all these centers and tells a story, and it has hypotheses, and it builds beliefs as to what's going on in the world. And the question is, how does this work? Well, here's one of the things we know about what evolution is pushing us to do. It is pushing us to take all the things that we do and drive them out of our conscious experience. You don't want to figure out how to throw a baseball or hit a golf ball or play the violin from the start every day. You want to get that practiced and part of your unconscious mind. And we realize that so little of what we do during the course of any day of our lives is really part of our conscious system, where things become conscious for a while, and then we practice them and we get them out of consciousness so that we can go on and deal with the new information that is being challenged to us at any particular moment. So the need for automaticity is clear, and the reason is consciousness takes time, and it can be demonstrated very simply in an experiment. If I put a light up and I want you to judge which light comes on before the other or what have you, a simple little discrimination, I can get your speed down to, say 200 milliseconds, 220 milliseconds, depends on the task a little bit. But I get you down to a baseline of 200 milliseconds. And then I say to you, okay, I want you to just slow down a little bit. Just kind of, don't be so fast. Just put a little 40 millisecond addition onto that thing. Try to respond around 260. And every subject says, no problem, I'll do that for you. You run them through the test again, and bingo. Their reaction time's now around 450, 500 milliseconds. The conscious loop has been kicked in. It tries to modulate this response. And in doing that, you're spending time because you're trying to do things through the conscious system. So you can't go through life like this. You got to get it out of consciousness. And the way this works and the reasons why are indicated here. But I want to give you two examples. One comes built in from the fact that many of our visual cueing mechanisms are built in in an evolutionary time just to work for us in a particular way. And another one is an example of how we learn something and drive it out of consciousness to be automatic. The first one the built-in one comes from Roger Shepard's famous visual illusion that I'm sure you've all seen in the psychology text. This is an example of two tables. They're both exactly the same size and length and width, and none of you believe it if you have normal brains, so don't tell me you do see it that way. And what you do is, so let me demonstrate that in fact you're suffering from an illusion that's been built into your brain as part of your temporal lobe, and you actually cut that baby out and put it over there, and you see it's exactly the same size. This is a great picture to use in a textbook. Students cut it up and makes the book used. Textbook writer here, I'm sorry. So these are the automatic ones that are built in through time and evolution, and they work just in this way. There's no amount of education that can prevent that perceptual event from happening. The ones that you and I experience and learn, of course, are things like typing. All of us in the room type. Some of us very fast, and you don't even think about it. You just know how to do it. So actually, this example, I may have to change this example, because actually very few people now in the younger generation know how to type. They know how to peck, but they don't know how to type. You know, I'm classic, old generation, can type 120 words a minute. Now, if you ask me where the L key is, I go, how do I know that? And I think through the board, I visualize it, and oh, there it is. But you don't think about that when you're executing all of this, just like you don't think about your language and so forth. So these things become automatic, out of consciousness, and trained. This even goes on in the neuroradiological suite. This is a study done by my colleague, Miguel Eckstein, where he looks at radiologists who are trying to judge whether there's a cancer present in women. And in fact, it turns out that the radiologists, as you can see, they vary quite a bit in their judgment, and they have to really practice at this. And so he did a study where he looked at a series of radiologists, and the question is, which group here would you think, these are the eye movements of radiologists looking at breast scans and trying to find the tumor. Which one of these two groups would be expert? Would this reflect the expert, or would this reflect the novice? And of course, you guessed it, the expert doesn't mess around with all that stuff he's learned, and he goes right for the tumor. So these things come in, they become automated, and then they go out of our conscious awareness. So with this, you get the idea that there's a modularity, there's tremendous independence, it's distributed throughout the brain, and in the presence of all this, there is this thing in the left hemisphere that I'm going to argue pulls it all together. And even though these things are going on independently and all the rest, it becomes to tell you a story that you're in charge, that you have a narrative, and we can all examine that narrative. So it goes like this. Again, the picture here of this distributed system, it goes like this. How did it come to be known that there are all these specialized brain areas that do specific things, and many, many more are being found every year? They're more complicated than indicated here in this cartoon. But it's the general idea that there's specific subsystems that do particular things. And it's a rich, interesting, fascinating neurologic story full of the greats in the neurologic world, from Thomas Willis and Francis Joseph Gall and Florenz and Jackson and von Helmholtz and Freud himself and so forth, Paul Broca. These people are all through the years made observations about how a particular lesion disrupted a particular kind of function. And while this was modulated and extended and made more complicated by many views, basically it set the framework for thinking of the brain as being a highly modular organ. And our own contribution came to it when many years ago, starting in the early 60s, Roger Sperry and Joe Bogan and myself at Caltech started to study patients who had had their hemispheres divided, the so-called split brain surgery. And right down the street, another major contributor at that time was Norm Geschwin, who made a similar observation on a clinical case. The experiments that Bogan and Sperry and I were surgical cases operated on. These patients were operated on in an attempt to control their epilepsy, to prevent the seizures from spreading from one brain to the other, and so forth. And our duty was to figure out what had happened to these patients, what were they like when their brains were divided, what kind of phenomenon could you see, was one brain knowledgeable about what was going on in the other, and all these other kind of spooky questions. And that was the first set of patients, and the second set of patients here were in the main operated right up the street at Dartmouth College with Don Wilson, Dave Roberts, and the neurologist Alex Rees. And I was privileged enough to be able to study both these series. And for the students in the crowd, I have to take a minute to tell you that not only is science one of the great ways to spend your life, but it's fun. You got to remember it's fun. And people sometimes think that science isn't fun, isn't inherently fun. Well, it is. And I want to tell you a story about this. Many years ago, we started to test these Dartmouth patients, and we felt deeply, at the taxpayers' expense, to have a fancy motorhome, to drive to their home, convert it to a laboratory, go up to their house, plug in the motorhome, and we could test the patient right there with them not having to travel to, at the time I was at New York, at Cornell. So Joseph Ledoux has become quite a famous neuroscientist, was a graduate student at the time, and postdoc later. And we were sitting around and thinking about, we had to write a grant, of course, to pay for this. And we said, why don't we throw that motorhome into the grant? Just as fine. So we put the motorhome, $32,000, and I remember the number at the time. And it came time to send off the grant, and I called Joseph in, and I said, Joseph, we need a budget justification for this motorhome. And he says, no problem. Now, Joseph is a gifted writer. And he came to neuroscience from a advertising program at Louisiana State University. So he whipped out this budget justification that apparently we learned after the judgment was made, sounded like Travels with Charlie. You know, there's just nobody could turn it down. And so we put the grant in. The grant guy calls back in that bureaucratic government voice that tells you you got a grant, or tells you didn't get a grant with the same evenness. It drives you crazy. And so this guy called to say, well, we're not funding the grant, except for the motorhome. So we got the motorhome, and we just had a wonderful time. And the other part, the fun part of it is I had to learn to park this 26-foot motorhome in this alleyway there on 78th Street and so forth and so on. So kids, it's fun. Okay, back to serious. So the first three patients that made up the so-called split brain patient were LB, and then a 12-year-old boy, WJ, who was a World War II vet, and an NG. And then the patients in the East Coast series from the Dartmouth were case PS, JW, VP, DR, and EB. These are fascinating human beings. None of them you would know had their hemispheres divided if you were sitting next to them or spending the evening with them or anything else. It's completely something that we can elicit, and I'm going to show you now how they behave. With special testing and being attuned to the nature of their surgery and what have you. So what the main finding of all the split brain work in the early years was the fact that there was this dramatic separation of function between the two hemispheres, as illustrated in this summary slide here. And it goes like this. If everybody in the room fixates this point right here. This word ring which is in the right visual field if you're fixating there, goes to your left brain. The word key in the left visual field goes to your right brain. You can see them both as key and ring and just say it. And that's because your corpus callosum, this thing right here, that connects the two hemispheres, is connected. And the information is transferred between the two sides. If your brain is split, you can only say you saw ring, because that goes to your left dominant hemisphere. So if I show this to you and you have a split brain, I say, what did you see? The patient says, I saw the word ring. Is that it? Yep, that's it. But with changing the way the test is presented, where instead of asking for a verbal response, you let the left hand, which projects its tactile information to this disconnected right hemisphere, left hand try to find the object that you've named here. You see the left hand goes out and can do it quite easily. So it's phenomenal that what the left brain knows, the right brain doesn't know. What the right brain knows, the left brain doesn't know. And that gave birth to a million studies over dozens of patients, and now well reported. It took us 25 years to ask the following question, though. This is another important thing for students to learn. You have a piece of data and information, and you study it, and you've got your head around it, and you explain it, and you're just as content as you can be with that information. And then one day you say, well, wait a minute, I forgot to ask the patient something. And you go back and you open up a whole nother piece of information and knowledge that you didn't have before. And in this case, what I'm referring to is that we again presented a similar scene like you saw before. Here we're showing a picture of a chicken claw to the right visual field, which goes to the left speaking hemisphere. And here we're showing a picture of a snow scene, which goes to the left visual field to the right hemisphere. Again, if you fixate there, you'll see both pictures because your brain connected. But if you're split, and I ask you to do this, you're going to say, what? I saw the chicken claw, because the left hemisphere sees the chicken claw, and that's all it sees. But again, if you don't ask for a verbal response, but you just say, point to what you see, that way either hand can now point to a picture of the object that matches what was seen by their half brain. So sure enough, the right hand, which goes to the left hemisphere, points to the chicken, which goes with the chicken claw. And the right hemisphere sees a snow scene and points to the shovel that goes with the snow scene. The patient's doing this in front of you, pointing to these two pictures. And you say to the patient, Paul, why did you do that? And Paul says immediately, oh, that's easy. Chicken claw goes with the chicken. This is the left brain talking now, right? And he looks down at his left hand, pointing at the shovel, and he says, and you need a shovel to clean out the chicken shed. So he immediately gives an interpretation of a behavior, an expression that is poured out of its brain, tricked by our methods that we know because of the surgery. Their brains are independent systems, and we can put a picture in and all the rest of it. But the idea is that there are behaviors pouring out mood states, actual motor activity going out all the time, and there's a system, one of the systems in the brain is building a hypothesis about what does it mean, what is the coherence. We've got to have a story here. We can't just have hands flying around without a coherent story. So enter the interpreter. And here's another example, actually, of an example that was taken a few years back with the assistance of Alan Alda, and I'm happy to say that the producer of that video series is here today. So thanks to him, and here it is. Here's another example so you see it in live.
Point to the word.
Again, Joe sees two words simultaneously. Bell goes to his non-speaking right brain. Music to his speaking left brain. When asked to point to a picture of what he saw, he chooses Bell. But when asked why...
Okay, why'd you pick that one?
Music.
Music?
And when asked to explain...
It was music and Bell, and
Those few minutes ago, last time I heard any music was coming from the bells out here. Banging away.
The bell's outside here.
So, look good enough answer to me.
What's extraordinary is that Joe's speaking left brain concocts a plausible story of why he pointed the bell, even when some of the other pictures more obviously represent music.
There's something, this left hemisphere's got to tell a story. It's got to try to figure out the pattern of activity in the world, pouring forth from itself, internal felt states. And I'll give you examples of those. And my colleague at Dartmouth, George Wolfer, thought of a little test that might show this same sort of thing. And it's basically asking someone to guess whether a light's going to come above or below a fixation point. Just say above or below and test each hemisphere in the same way by testing either the right field or the left field. And in fact, the light would come on either 70 or 80% on the top in the experiment. And what the normal person does, what you would do, is instead of just always picking the top button, which would maximize your reward, if you just always picked it, since it goes up there 80% of the time, you'd win 80% of the time. No. We all go to colleges like Holy Cross and so forth, and you try to figure it out, right? That's what your parents are paying these people to do. Figure out the story, the pattern. So you start to guess. And of course, you completely mess up and you score around 67%. If you give the same test to a rat, the rat does not make that error and goes straight to the top button and just parks there and hits it away 100% of the time and gets 80% of the reward. So we did this in the split situation, and the right hemisphere acts like a big rat, and the left hemisphere tries to do the fancy stuff that we all try to do. Have a hypothesis about the meaning of what's happening, and in that hypothesis, of course, makes mistakes. An example that shows the ubiquitousness of this, I think, comes from a classic study done several years ago in social psychology, done by Bob Kleck and Chris Strenna. And it's the scar face experiment. What they did was subject had a scar painted on the face, and it was put there with the idea that they were going to learn how someone they interview might be biased by having a handicap, a distortion of their face. And they wanted the subjects with a distortion on their face to come to understand what it may be like for people with some kind of disfigurement to interact with the regular population. So that was the ploy. And so everybody understood and so forth. And the subject was about to go in for this interview with the other person. And the experimenter actually says, well, we just have to put a little something on that scar to hold it so it doesn't kind of ooze when you're in this hot video booth. So actually what they do, unbeknownst to the subject, is clean it off. There's nothing there. They're clean as a whistle. But the subjects all go in thinking they have the scar, and they interview, and every subject comes out. Every subject. This is not a statistical phenomenon. They come out and say, oh boy, I never had any idea what people with, a little disfigurement have to go through. And the examiner says, really, is that true? Yeah, oh, it's just terrible. It's just, jeez. And so the examiner said, well, actually we took a video of the person you were interviewing, and maybe we could show you that video and you could show us where you thought they were showing a discriminatory response. Fine, show it, bring it on. And so he would show this video back to the subject. And I mean, it was just a couple seconds in, and the subject would say, see, stop, look at the way he's looking there. You see? That's why. They come up with an explanation, fitting the situation, etc. So there are many demonstrations of this, the ubiquitousness of this thing working in psychological life and everyday life, forming hypotheses and having an effect what you think is going on in the world. Another example is done by Metcalf and Fennell, where they would show somebody a little story. Let's say somebody waking up in the morning, going through the motions, getting dressed, getting shoes on, having coffee, going to work, etc. So it was a storyline, 40 slides or so long, just a little story about someone basically going to work. And a couple hours later, you would either show that the subject one of the actual pictures that was in the story, a picture that had nothing to do with the story, or a picture that could have been in the story, given the gist of the story, but in fact wasn't in the story. So you have these three conditions, and then you ask each hemisphere, each half brain, what did you see? Can you detect the related from the unrelated from the distractor? And it turned out that the right hemisphere simply was a whiz at detecting the studied picture, but the left hemisphere, and rejected all the others, and the left hemisphere included in what it saw all of the related pictures. In other words, it said, oh yeah, it was something about a guy getting up. Yeah, that picture could have been in it. And that belief, that larger interpretation of what actually happened, guided the future information and changed the criteria for what was believed to have been presented or not. So this really is a story. There's something in there, no matter how you look at it, that is continually trying to figure out the pattern of responses that are coming out from these many, many modules, these many, many different systems, and pulling it in to a story. And there's one other example here that comes out of the work. Walter, I forgot, are you going to present this study? You're not. So working with Walter and Mike Miller, we looked at the example of, with all of the interesting work going on moral reasoning, could it be that a split brain patient might act differently in a moral judgment task, as we have come to learn through a whole set of work that I'll just mention briefly, that aspects that go into a moral judgment can be processed by parts of the brain that might be separated in a split brain patient. So what would the nature of a moral judgment in a split brain patient be if all of the processing sites that contributed to a coherent moral judgment were not available to the decision system? And so we looked at this in a variety of patients who have disconnections of both partial and complete, and just asked the question, is moral reasoning disrupted in these cases? And the findings were striking. There is the belief that as I come to understand your felt state, I do that by simulating in me how you feel. So the way I come to understand your position is I have to simulate your emotion in me, and I feel it that way. So you get this sort of notion that I can believe that hurts you because I actually feel the hurt. But what about you want to manipulate the belief in the other guy's head to your own good, right? You have a belief about the other person's belief, and that belief is going to be important in you making a subsequent judgment. So predicting mental states of others, this turns out to be derivative from the findings of a few years ago, 20 years ago now. Time flies when you're having fun. 20 years ago, that people can hold false beliefs and believe them that they're being held in another person's mind. In other words, you have a theory of the other person's mental state, and you're manipulating that theory as you deal with them. And I'm not going to go through that experiment because it's really beside the point. But all this is summarized to show, I always do too much, to show that the part of the brain that may be involved in the processing of the belief of another person is something that's in the right hemisphere, as opposed to this talking, interpreting left hemisphere. So what would you predict? If there's a split brain subject where these two systems are separated, you're going to probably have a conflict in the judgment. And how would that play out? So this is the experiment that was done, and it goes like this. So the question again is that through a bunch of studies I didn't tell you about, there's this part of the right hemisphere that is active in assessing the beliefs of someone else, and you need those beliefs when you're making a current molecular, a moral judgment. And so here's how it worked. Susie here wants to get some coffee for her boss, and Susie puts some sugar in it and takes it to her boss. The boss drinks it and he dies because, in fact, the sugar was toxic. So you give this sort of puzzle to people, and which was obviously an accident, and you say, is that action permissible? And everybody in this room should say, well, yeah, it's permissible because she thought it was sugar, and the fact that it was poison was unknown to her. Okay? The contrasting case is that Susie goes to get coffee for the boss, and actually Susie's a little annoyed with the boss and hopes it's toxic, and finds out that, in fact, it was sugar, and the boss lives. Very annoying to Susie. And the question is that action permissible? And you and I would say, no, because the intent there was to kill the boss. Well, this same test, so that's called the normal answers. I gave them for you in case you were on the line about any of this. I don't want to embarrass you. But it turns out, to enormous surprise, you give this test to split brain patients, and what happens is, because the decision centers on the left can't access the actual belief of the other person, that they only assess, and this is just the split, their MRs and blah, blah, blah. They only assess the outcome. If they only says, well, if the outcome was good, it's okay. And they don't take into account this information that seems to be localized or isolated in their right hemisphere and not able to participate in the decision-making system of the left. Now, that's the prediction, that's the result, it's kind of unbelievable. But here's the important part. Interpreter to the rescue. So these split brain patients are normal old folks just like you and me. And they now have had this bizarre kind of answer come forth from them. And their interpreter has to go to work to pull this thing together to make it seem sensible. So here's an example of what they do. After hearing a scenario in which a waitress knowingly serves sesame seeds to somebody she believes is allergic to them, yet the outcome was positive because the person turned out not to be allergic, JW judged the action to be permissible, right? One of those crazy responses, practical answer. Moments later, he rationalized his response, sesame seeds are just tiny little things, not going to hurt you much. So out came this behavior produced by the result of this surgical alteration where the information wasn't being normally synthesized. But there's this interpreter keeps trying to pull together the story to make it coherent, whole, and of purpose. So here's what I'm building to. And this is one of the major, I would say the major aspects of studying neurologic patients and other kinds of patients as well, but I concentrate on neurologic patients, is the incredible amount of self-cueing that goes on to always make it look whole and of purpose and worthwhile. So you've got this belief that everything's unified. We all have it. may be precipitated by this interpreter, like I'm trying to argue. But it's trying to manage this vastly parallel and distributed system where stuff's coming out at all times, and it wants to pull it all together into this coherent view of purpose. And when you look at that, you say, well, there's independent action with this appearance of unity. How are the many ways that we might see that you could now interpret if you have that view? So I'm going to show you three, and then I'll wind up. I'm going to show you a most incredible one where there's integration of the disparate output from two different systems on a piece of paper, and yet the system blends them together into this whole. There's integration of information when it has to get together inside the brain, and that precipitates a model about how we should think about all of our ability to be consciously aware of this stuff. And then there's the implication for the social world. How do we really coordinate our mental lives with other human beings? And in the end, that's what the human's all about. It's all about theory of others, not particularly about your own theory. So first, the outside, the brain one. Now, you've had my little mini split brain stories we're going along here. So let's see if you follow this. There's a split brain subject. This callosum is cut. And what we're going to do is we're going to put the word 1928 into his silent right hemisphere, right? 1928. And we're going to put the word car into his left hemisphere. So you will know, if I just asked, this is case JW, if I just asked JW, what did you see? He said, oh, I saw the word car. I didn't ask him. All I did was say, okay, draw what you see. So now with his right hand, he's going to draw what he sees. And the only thing he can consciously report is the word car. Watch what he draws. The first part of this video is not, the light was bad, but you'll see the end product here in a second. J.W. was quite an artist and quite a car aficionado. Somehow, I'll just tell you a running story here, somehow what you will see in a second is that he draws a 1928 car. Now, how does he do that? The arm is changing controls between the hemispheres. The hemispheres have not mixed this information. The hemisphere that saw a car didn't see 1928 and vice versa. So somehow that information is being integrated as kind of like, and let it all hang out there and we'll get this thing pulled together somehow. And incredibly enough, you see exactly that. That there he has drawn this car of the right vintage and the like. This is pulling it together when the information is emanating from you, but can still be modulated in ways that are complex, too complex now for us to figure out. But you have the actual behavioral product showing the way. And these two examples on the left are the exact same thing, just using other stimuli. Give you another example. A couple of the patients go on to show speech out of their right hemisphere as well as their left hemisphere. And how that goes is simple. You normally flash, say, a picture of a key to the right brain and a picture of a fork to the left, and the patient would say, I saw a fork. That's the normal way things work in a split. By now, you should be clear on that. All of a sudden, you go in the lab one day, and the patient says, fork and key. And what? What's going on here? And first thing you do is say, okay, don't tell me what you saw. Tell me whether they're the same or different. You just said fork or key. It's obviously they're not the same. It should be an easy task. They can't do that because there's no sensory integration here. What's happening is each hemisphere is simply responding. One says fork, the other one says key. And it looks to you outside as wonderfully integrated, but in fact, that is what's going on. Okay, so now you have a left brain that's doing the major talker, and now you have right brain just throwing in a few words every once in a while just for the fun of it. And you can see it here. Here's the case VP, who is a person, one of the patients who developed ability to speak out of either hemisphere. And we're giving what we call a split word test, where we're going to show her the word breakfast straddling the midline, which means the right hemisphere is seeing the word break, and the left hemisphere is seeing the word fast, right? But in fact, normally, it would appear to be the word breakfast. So here, watch and listen to what she says.
Just go ahead and say that first.
Okay.
Does that make sense?
Yeah, it's still supposed to make a word?
No.
It doesn't necessarily have
Doesn't
to?
won't necessarily. So,
Okay.
like for example, with honeymoon, if you saw moon first, just go ahead and say moon, honey.
Okay.
Doesn't.
Okay. That hasn't happened yet. But
Okay.
If it does, I surely will.
Okay.
Break and fast.
Okay.
Hot dog. Flap. Jack.
Good.
Hamstring. Am I doing this right?
Perfectly.
Okay.
I have one other
Because I
question.
didn't know if I should say that
Yeah.
word first.
Nope, that's fine. Whichever one you feel like you know first.
Okay.
So I have another question.
Mm-hmm.
When it was breakfast,
Right.
you would pronounce the word break as break,
Right.
unless it was part of breakfast.
Yeah.
Do you know that it's a break first, or do you know that it's breakfast first?
I know that it's break first.
Okay. And
But
then
I
you
know
make
it's
it
supposed to
into-
be the word. So
Okay.
I
So it's
have
when
to,
you get the second part that you change the
right.
first.
Otherwise, I just see break. It would be like break and fast, but it's supposed to be one full word, so I make it breakfast.
So you get the idea that break and fast, but she knows, she's a smart lady. Well, they're supposed to be reading words across the midline. If it's fast, it must mean break, not break, and so forth. And she puts it, but self-cueing to make the whole, to make it all seem normal, to make everything just as we want it, that we're in charge. Another example, here's a story given to another patient who developed speech in each hemisphere. And you read it one way, the story just simply says, Mary Ann may come visit into the township today. But now that you're all split brain aficionados, you know what's going on, is actually the right hemisphere sees the story. Mary may visit the ship, and the left hemisphere only sees the story, Ann come into town today, okay? So that's where it is in the brain. But now we're asking for behavior to pour out, and you can see everything being cross-communicated and the narrative built. Ann come into town today, that's what the subject says. Anything else, I ask? On a ship, who? Ma? What else? To visit? What else? To see Mary Ann? Now repeat the whole story. Ma to come into town today to see Mary Ann on the boat. So, it's eerie. And these are all experimental tricks to perhaps cue on what we're doing. I mean, as we're saying things, these words are coming out, and we're alert to them, and we try to clean up our syntax on the fly, and we do all these things. It's all self-cueing to maintain the whole, that it's all integrated when it's really coming from this vastly parallel and distributed system. And I'm just going to skip that one in the interest of time so we can get to the last one. So, interpreting moment-to-moment activity. We're going to do an experiment right here in this room to show you how your brain is constantly changing between states, and yet it appears to be, you have this sensation of being consciously whole. Here's the Michoud ball attribution test. And this is a very famous test of what's called studying perceptual causality in the area of perception in psychology. And as you all know, that if you've seen this lesion here where if one ball comes and touches the other one, you have the sensation that the other ball was hit, like a billiard ball, and there's causation, and the other ball moves. And then, of course, the psychologists come along and they break down this illusion by beginning to manipulate things. So instead of the ball actually hitting the other ball, it stops before it. And they do this so it stops further out, and pretty soon the illusion breaks down that there's a causal relationship. Or you do it temporally. You let it hit the ball, but you delay before the other ball leaves. And again, it's all a way of seeing how far can you push this before this illusion falls, what part of the brain is doing this. And Matt Roser and colleagues studied this again in the split brain population and found very clearly that it is the right hemisphere. When you are seeing that illusion, it is your right hemisphere that is processing the information as you sit in this room. Because you can test a split brain patient and give this to both hemispheres separately, and the left hemisphere simply doesn't respond to this test. It doesn't know what you're talking about. It just sees the phenomenon, but it doesn't have the phenomenon. You take another test, however, and here you want to see if the right hemisphere can make an inference about something that's more logical. And again, just using visual stimuli. And you will see in this test, there's a very simple task where a green line goes down and hits the bottom box, and the bottom box lights up. When the red one alone goes down, it doesn't. But when green and red, it does. So what does the red do? The red doesn't do the trick. Very simple little first grade task, right? Right hemisphere cannot figure that out. Cannot figure that out. Left hemisphere does it instantly. And so as you just sit here and do that, the conscious processes that are involved, and you're phenomenally aware of it, have got to be associated and localized to those hemispheres as revealed by the results in the split brain patient. So things moving around, constantly moving around, and yet and we keep this narrative going that it's all coherent and coming through a common processing center. Okay, so finally, let's move and really kind of setting up my colleagues and their upcoming talks. Psychology has been centered on the individual for years. There's been a classic psychology of social psychology, of course. But the real question is, how do we get along? The real big deal with humans is our social interactions. That's what this big brain is for. It's calculating all of our codependencies on others. We're in the middle life of others. This is what we think about all day long. You don't wake up in the morning and think about triangles and squares and stuff. You think about your boyfriend, your girlfriend, your mother, your father, your priest, your whatever it is. Their intentions, what's going on, what do they want, right? It goes on constantly. We're flooded with this. And so we have developed in the past few years through the work of, it's a small cottage industry now, but I'll give you the primaries in a second. Theory of mind. We have theory about the other person's mind and intention. So it's more of a theory of mind. I like to call it theory of others. And it can be illustrated simply, the fact that we as a human, our species, you and me, map kind of agency on almost anything that halfway resembles animation. And here's an example of someone visiting COG, the robot at MIT. And this thing, even in its simplest form, could follow you around, or you walk in and it would follow you around, you sit down, it would look down on you, and it was very creepy. You know, what is this thing? And soon enough, you began to say, well, you know, that's COG. How's he doing today? You know, that's the thing. Right? You have a theory of him, and every time it moved its eyes, it triggered in you the image you had of it. So you're carrying around this big idea about it, and it cued you every once in a while to respond. So you have a big theory about that. And is there any wonder why in these life-death issues, as seen here, that there's any surprise that excuse me, a mother would not see their child forever with a flick of an eye, even though the underlying neurology of the child may be disastrous. Because it's the model in the person, the mother's head, that she's living. And any cue to reinforce that model is going to be active in her, and that person is as alive as anybody. And so it's the mental model of others that lives in our minds, and that, of course, doesn't die when they do. So, I don't know, I should take that out of there. I met this mortician, and those are funny people. And anyway, he pointed out the dead don't care, so I don't know, life and that. So the person who got us in psychology in modern times to think about this theory of mind really was the psychologist David Premack, who worked for 20 years of his career on chimps. And he finally decided that they didn't have a theory about him, but he had a theory about them. And so this comes down to the well-known, more practical, that you have a theory about your dog, but trust me, your dog does not have a theory about you. And it's the theory of the other person. It's the theory of building up a story about them and their intentions. That is what we humans do all the time. It's so crucial for our understanding and mixing and being part of a social group and all the rest. And so Premack's psychological formulation of this and his extensive work on it was augmented in about 15 years ago by the fascinating work of Giacomo Rezolati and his mirror neurons. Giacomo is an Italian neurophysiologist, lives in Parma, and I had the privilege of doing my postdoctoral studies with him in Pisa 347 years ago. Never mind. But he is an extraordinarily creative man. And anyway, he was he just had the following idea. He was recording from the area of the monkey brain, and he noticed basically that the monkey, this particular set of neurons he was studying, responded as the monkey grasped the neurons, not as the monkey moved his arm to go to the neurons, not when the monkey fixated and looked at the grape out there. So there's a grape out there, and when the monkey looked at it but didn't do anything, when the monkey moved his arm it didn't do anything. It's actually when the monkey grasped the grape did these set of neurons that he discovered fire off. Well, now most people would have stopped there. So yeah, that's pretty interesting. Whatever that is, that's that. But Giacomo had the good sense to continue and be recording these neurons, and instead of the monkey touching the grape, the experimenter touched the grape. So now a human is about ready to touch this grape, and the monkey's neurons are going nuts. They're responding. And this intricate series of studies over the last 15 years, all of a sudden, is it building a platform for the animal is processing the social interaction, the state of the common act in the community. And so Giacomo was kind enough to send me this little film clip that shows this so you can just see it and have a sense of it yourself. I'm almost done. So there's a neuron going, the monkey picking up the grape.
Fanno un altro così. Come prima, feeling. Ancora.
You don't see that very often. It's something just like that, just so clear. Anyway, so that gave rise to the whole concept of mirror neurons, of the cortical building blocks is the idea for this thing that you and I do reflexively, which is build a model of the other persons and their actions to be in common with us. And And so what I'm suggesting is, and I'm just going to move on to this. What I'm suggesting is that we have this queuing that goes on to constantly pull together the theory, the idea that what we're doing is unified. We can see it within the various brain manipulations I've discussed within a person. We can see how we try to do it even when they're pouring out to the outside world, and we're adjusting them as they go to keep the theory going that there's a unified person. And what the excitement of social neuroscience is that we're beginning to see how we guide ourselves in this social maze of interactions of people so that we can communicate and be understanding of their points of view and respond to them in a normal way. The experiment that is consistent with this mirror neuron story and the theory of mind story, and I'll end on this, is just to give you a feel for it, for those of you who have not studied all these matters, is the work by Jackson and colleagues, Desity and so forth, Meltzoff, where they basically looked at pain in an MRI in a brain imaging environment. And I could take you and introduce pain to your hand by just squeezing it harder and harder till it was kind of hurt, and then it really hurt, kind of a gradation kind of thing. And we look at your brain, what's happening, and we can find your brain pain circuits, and we can see the intensity of the response in your brain is modulated by how hard we're squeezing you and so forth. And then, so you get that picture, and then what you do is you put another group of subjects in the brain imaging environment, and instead of actually pinching them, you show a video of somebody else almost getting these various gradations of pain. And it turns out your brain lights up as if you were actually having the pain. So the notion is that could this be another one of these mirroring systems where you understand the other person's felt state because you are experiencing it. And that is how you come to understand the other person's state. And that what we are doing is constantly modeling the world of others to fit our own world that we're modeling and blending that information so that we can function in the social world. And so what's happening now is there used to be a standard summary slide of all the personal cognitive things that were distributed around the brain that came out of split brain work, other neuroclinical work. And in what's being developed now, I think from the people who are taking the social aspects of our life, which are so important, and putting it into the research environment, is showing again how all these complicated social things are also distributed, some of them bilaterally, some of them modularized, and and singly represented in one hemisphere or the other. So we are this automatic parallel machine that is doing all these things, and our conscious awareness of being unified is a theory built up by one of them. But when we're actually conscious aware of any one particular one of the specific domains, that's where the system is at that moment. So it's kind of like a pipe organ playing, is the metaphor. It is not that everything gets done and then goes through the conscious enabling center. It's a parallel distributed system, complex, figuring this stuff out. And one of those centers tries to tell a story that it's unified, but in fact, it's not. So I'll leave you with that thought. And again, Tom, thank you for the opportunity.